In CS109, we learn about logistic regression, which allows us to take a set of inputs, derive a series of weights or thetas that correspond to different features of an input set, and predict some binary output for each member of the input set. But what if we wanted to predict something which isn't binary, like hair color, or geographic location, or disease outcome? For example, breast cancer, which 1 in 8 women in the US will develop within her lifetime, has a myriad of outcomes. 1 in 3 women with breast cancer will go on to develop what is called a metastasis, which is breast cancer that occurs somewhere else in the body, like the lungs, liver, brain, and many other possibilities besides. In this case, if we wanted to predict disease outcome, we would need a method that accommodated more than just 2 possible outputs. Welcome our new friend, the Multinomial Logistic Regression, who looks a little something like this. We start with some input matrix X, which consists of n patients, each with F features that we want to examine. We multiply this matrix by some weight matrix, which consists of the weights for each feature towards some particular output class. This multiple gives us Z, which we can think of as a non-normalized probability matrix. To squash our function, we use the softmax function, which is analogous to the sigmoid function in our binary logistic regression. Finally, we use our familiar pal argmax to determine which outcome is most likely for each patient, and we're done. To derive our gradient descent optimization, let's work backwards. First, choose any person I and class K, and we see that the probability of that person's outcome being yi, or that class, given their input and the weight matrix, is the corresponding probability from the previous matrix, which is the softmax of the corresponding value from the Z matrix, which is given by this formula. Now, let's extend this to all people. The probability of y given x and w is the product of all these observations, since each person is independent. So, we take the product of all these softmax results. We can now calculate the loss function using the negative log likelihood function and normalizing by the sample size. Using our softmax expansion, we get this very nice summation. And finally, we can calculate the gradient of the loss function with respect to w, using our normal derivative methods. Notice that there is a new identity matrix included here. This is called a one-hot encoded matrix and serves as an encoded version of the Y, or the outcome matrix, where instead of being a single column matrix with each entry indicating the class outcome of that particular output, each row now instead has a 1 in the index corresponding to the class outcome of the input, and a 0 at each other index. We can represent this using the encoded subscript on our matrix Y, and we have our final gradient formula. So, how would we translate this to code? Well, we can follow a very similar procedure to binary logistic regression. First, import a dataset and format it as an input matrix X and the class outcome matrix Y. Then, generate an initial weight matrix W of an appropriate size with all 0 inputs. Next, we multiply X and W to get Z. We apply our softmax to Z to get P. We use these previous components to calculate the gradient descent of W and update W according to our formula, and we repeat these steps many, many times. When we run our code using a breast cancer dataset to predict metastasis location on the basis of various demographic and genetic features, we get a 35% accuracy rate. Not horrible, considering our dataset comes from a real-world experimental study and is restricted by sample size and applicability to our question. At the very least, this result serves as indication that such a question is worth studying further using multinomial logistic regression, and it demonstrates that difficult medical problems could potentially be solved with the kind of math that we learn here in CS109.